Welcome. Example 0 here, and as with all example zeros, this is a theory video, which is that we're going to explain why this formula is what it is. Yeah? Okay, cool. And also before I start, very quickly, I think that this is the best explanation of the fundamental theorem of calculus anywhere on the internet. So if you can find a better explanation, then I will tutor you for free for 3 hours. That's a promise. Okay. And second is that on a lot of online reference material as well as books, you'll find Fundamental Theorem of Calculus Part 1 and Part 2, but no such thing. Like the Fundamental Theorem of Algebra or the real Slim Shady, there's only one Fundamental Theorem of Calculus, and that's this one right here. Yeah? Okay, cool. In fact, this guy here, which is supposed to be the other fundamental theorem of calculus, is actually called the Evaluation Theorem. And look at it. It makes perfect sense that it's called the Evaluation Theorem. It's not a misnomer. It evaluates integrals. Alright. Now, let's explain the fundamental theorem. This guy, right? So one simple, basic explanation is that what is happening is that you take the integral, right? And then you take the derivative. So the derivative of the integral should be the original function. Because, like, we can think of integrating as a backward movement. So if you move backwards and then you take the derivative, which is that you move forwards, then you should end up where you started, right? That's kind of a cheap but simple explanation. Yeah? But you still have some lingering questions like, that's a t, that's an x, and so on. And this is a very basic explanation. So here's a slightly better second explanation, and we'll offer more. And the slightly better second explanation starts with the integral. So if we look at the integral from a to x of f of t dt, oftentimes, like the evaluation theorem, there's a small statement that accompanies the fundamental theorem of calculus. And it's the same small statement as the evaluation theorem, which is that capital F prime is equal to little f. Notice that this statement is equivalent to saying that the integral of little f is equal to capital F, right? That's what that's saying. So then I know that this here is equal to capital F of t evaluated at a and x. Well, how lucky that we have the evaluation theorem handy, because then we could write that this here, which is equal to that, is the following, which is capital F of x minus capital F of a. Now, notice that capital F of a is a constant. It's just a number, because a is just a number, and we've plugged a into capital F of t, and therefore this is just a number. Got it. And also notice that there's a ddx in front of the integral. So we need to write ddx here, which would mean that we'd have to do it here. Which should then mean that we'd have to do it here. Now, this is the same as that then. And if we look at this, it's saying take the derivative of that and that. That's what ddx means, right? Just take the derivative of. Well, fine. If we do it in order, take the derivative of that, it'd mean we have capital F prime of x, and then minus, we've already said that that's a constant, so the derivative of a constant is 0. So why bother with the minus 0? So that's it. But wait, capital F prime is little f, and it is of x, so this is f of x, as we should have on the right side of the statement, right? Cool, right here. So that's a second explanation. And here's a third one. And this third one requires that we go back to the definition of a derivative, right? Remember, if we have a function g of x, then the derivative, g prime, is defined as limit, right, as h goes to 0, of g of x plus h minus g of x all over h, right? That's the definition of a derivative. And ddx, as we've already said, is saying take the derivative. Take the derivative of what? Well, the integral from a to x of f of t. So why don't we say that g of t or sorry, not g of t, but g of x is equal to the integral from a to x of f of t dt. Now, notice that g is an area function. So what it does is, we've got the curve f of t here, and I just drew a generic curve, like it could be anything. But yeah, I just drew one possible, visual of what f of t could be. So you have that, and so then this here is saying like, it's an area function. It's gonna tell you the area from some t value, and this is a t-axis, right? Some t value called a to x, and like depending on x, obviously you get different outputs. That's what g does. Got it. And I don't want to over-explain that, but now what we have in writing d dx of the integral is basically g prime, right? So g prime would be d dx of the integral, right there. Okay, d dx of this. Got it. So that's pretty much all we have to do to find g prime, right? In other words, to find d dx of the integral. All right, cool. And remember again, g was this guy. Okay, cool. So then we should write the g prime or d dx integral. So g prime is, by the definition of a derivative, it's equal to limit as h goes to 0 of g of x plus h. Well, if this is g of x, what would g of x plus h be? Well, g of x plus h would just require that we replace that there with an x plus h. So g of x plus h here, I'm going to write next as integral from a to x plus h of f of t dt. And then we have minus g of x, which is just the integral from a to x of f of t dt. And we have that divided by h. Got it. Okay. So we have this divided by h. And then we just have to figure out what that is. Okay. Alright, cool. Now, let's look at our numerator. This guy. So that numerator, and I should get rid of this t-axis label and put it on the other side because it's getting in the way kind of. So there. So again, if we look at this numerator here, notice that by the evaluation theorem, this part here is going to just be f of x plus h minus f of a. And then we have minus this part here, which we've already dealt with by the evaluation theorem, which is f of x minus f of a. And when we distribute this minus sign, that guy's going to become negative and that guy's going to become positive. So we could just write it with that. So from what I just said, that's minus f of x and then plus f of a. Okay, and this here, all of that is a replacement for this numerator, right? Okay, cool. And so we still have divided by h, and we still have limit as h goes to 0. Okay. And then we have lim, and this is supposed to be g prime of x. Yeah? Okay, now obviously this guy and this guy are going to cancel. So what we have for g prime of x is the following. We have that it is equal to, if I get rid of that, and I get rid of this, right? They canceled. It's too big. Scoot this guy a little closer to that. Do the same with h. Make it more central, right? Guys, what in the world does this say? Clearly, this here is using the definition of a derivative on capital F. So this is equal to f prime of x. And so therefore that's f of x. In other words, g prime, which is d dx of the integral from a to x of f of t dt is equal to f of x. Yeah? Cool. Alright, so I think we only have one final explanation left, and this final explanation, our fourth one, is going to be a visual explanation, and probably the coolest one. actually want to keep that quotient there, so let's keep that quotient there, and let's actually slide it to the left here. Remember, this here is basically the statement of the fundamental theorem of calculus recast, right? Okay, alright, because it's saying ddx of the integral, right? And that's the way that we'd written g. G is still, and this here, g is still what we said it was, which is, it is the integral from a to x of f of t dt. And therefore, g prime is this here. Yeah? Okay, cool. So, let's think about this visually. And before we look at the limit, let's just look at this quotient here. And so that quotient there is saying take the difference between the integral from a to x plus h and then the integral from a to x. So first, notice that a is a constant, right? So like once we say a is here along the t-axis, it's there. It's fixed. So we're saying that it's there right now. And we could have chosen a to be 0, but we want to make it more general. So I like where we chose it. Now, x could be to the left of a or to the right of a. So the analysis that we're going to do doesn't assume where x is. But for the sake of simplicity and ease of visual, let's pick x to be to the right of a. So let's say x is like right here. Got it. So then the integral from a to x of f of t dt is fairly straightforward. That there has got to be the area bounded by the x-axis, the red curve f of t, and then the two vertical lines x equals a, or t equals a, sorry, and t equals x. So it's this area here. That's this part, right? Cool. What about the first part before it, which is the integral from a to x plus h? Well, that's the same interpretation. That's an area, right? But the area from a to x plus h. Now, h is often some small positive number. So let's assume, that we stay consistent with h and make it some small positive number. Then we're claiming that x plus h would be like right here. So let's make it there. So let's propose that x plus h be there. Fine. So this here is x plus h. Then obviously the area from a to x plus h, this part now, is going to say all of this area. So our numerator is the difference in this area that I just shaded and this area, which again is that part. And so then our numerator is this area right here in between, right? This area here. So that's what our numerator amounts to. And our denominator is obviously the length of the interval from a to x plus h, so it's that much. So this numerator here is this area that I've shaded in here. And then the denominator is h. Now, let's go back to some basic geometry. Remember a trapezoid, and let's pick a right trapezoid because it's appropriate for this situation. A right trapezoid is just a trapezoid with a right angle. Okay. Alright. And I do a geometry proof of this in my geometry videos. But if you have a right trapezoid, and this is true even if the trapezoid wasn't a right trapezoid, it's just that a right trapezoid is appropriate for our situation. Then this line that I'm drawing right now, I was trying to draw, this line here, is called a mid-segment of the trapezoid, also a midline, also a median. It's got like 3 names. Anyway, a trapezoid has 2 bases, and they're the parallel sides of the trapezoid. And so let's say that smaller base is A and that's B, and this is the height. It's just so I've rotated it from how it normally sits. Anyway, now the area of the trapezoid would be A plus B divided by 2, so the average of the bases, times the height. And the weird part, or the cool part, not weird, cool part, is that a plus b divided by 2 is the red line. It's the midline. So the area of a trapezoid is this middle line, or that mid segment of the trapezoid, times the height. Right? Cool. This is important, so pay attention. That's the area of a trapezoid. Got it. Now, so then if this is the area, notice that if I did the area divided by h, then I'd get a plus b over 2. So when I divide the area by h, I get the midline. Alright, so we can see that, like, even if it's not a perfect approximation, that the area that I've shaded in white here is approximated very well by a trapezoid. Exactly the kind of trapezoid that I just drew. So let's draw what would appear to be the midline, which is that right there, right? And obviously I'm treating it like a trapezoid, but you know, it's not, but it is if h is arbitrarily small. We can pretend like it's a trapezoid, right? So I've got that midline right there. Cool. Now, our numerator is saying the area there. And then our denominator is dividing it by that there. So it's the equivalent in this trapezoid example of doing the area divided by h, which, as I said, gives you the midline. In other words, this whole thing here is an approximation of f of x through the midline. So right now, the best that we can do to estimate f of x, and by the way, f of x is this green line right here on the left, right? Directly, like, vertical from where x is, right? So we're saying that the value of that segment right there is best approximated by that red line right there. However, we're evaluating the limit as h goes to 0. So as you can imagine, as x plus h moves closer and closer to x, and let's put it like right there, for instance, let's say x plus h moved at some point to this, you can see that that midline would also move with it. So then the quotient that we have over here, this guy here, will continue to approximate the midline. It's just that the midline here now is going to be that. As soon as we move x plus h from here to here, the midline also moves, right? As you can see, when h gets arbitrarily small, so that x and x plus h are like arbitrarily close to each other, that midline will continue to be closer and closer to, you got it, f of x, that vertical line. And so, in theory, when we actually evaluate the limit, it will be exactly equal to f of x. And so, this is my my fourth and final explanation. Yeah? Cool. I hope you appreciated this, and I'm going to have several well-picked examples that are going to, like, basically have all your bases covered, regardless of how hard your class is. I'm going to do very easy examples and very hard examples in a few videos to come. I don't know. I haven't decided how many examples. Probably like 4 or 5. Yeah? So keep watching. Take care.